is prepping their microplates for microgravity. Microplates are also used in labs on Earth, but these were specially designed to be self-contained.
My role on the project was to design the actual microplate themselves. The challenge on orbit, though, is that generally fluid experiments have to be conducted in the glove box, and the glove box is very time limited. It's very crew intensive. So we've designed this self-contained microplate that can be operated outside of the glove box. It has all of the containment to keep the fluids inside.
So we have loaded these wells with hydrogels that they were carrying drugs, and we want to actually look at the effect of microgravity and how the release of the drug is affected when we send it to the space station. So the concern that we have is that if we have bubbles that are in the wells, it may be difficult for the plate reader to be able to read the amount correctly. So we are being very careful with how we are loading the waters.
So what's left to do today, once Stu here finishes filling the microplates, I'm going to take over and seal them up completely. Once that's done, we'll add all of the labels onto the microplates and put them in a self-contained box that is what they'll actually travel to the space station on.
3 years in the making just to get here.
Once we do that, we'll turn it over to cold stow. Cold stow will take it from there, and the next time we'll see them, we'll be on orbit, and the crew's opening them up.
Cold stow, short for cold stowage, is the team responsible for making sure that the research stays at the right temperature on its journey from the lab on Earth to the lab in space. This handoff is one of the last steps before being loaded onto the rocket. The cold stowage team will take Elaine and Stu's experiment and keep it safe and sound before it's loaded for launch.
Does it feel like a relief?
Well, it'll feel like a relief when we actually see it take off. And then it'll be finally...
It's a huge step though.
Yeah.
It's done. It's out of our hands at this point.
Yeah. It'll be officially out of our hands when it leaves the Earth's surface. So that'll be the moment that we're finally done.
That's just the beginning, actually.
So what'll happen now is, now that we've handed them over to NASA, NASA will deliver, they're on their way right now out to Dragon to be loaded. And the launch hopefully will happen tomorrow at 13:38. I've been involved since the very beginning, which is approximately about 3 years ago. It's been a long road, but like everything, it's a lot of work. It's worth it, and we're excited to help Timpanogos and get some data for this project.
Overall, we're going to get a lot of data from just this one project, and those 2 experiments that are going to inform a lot of different things for us. All right.
It's a little windy out here today. It's a beautiful day. It's a little windy. It's got me concerned. My launch intuition is tingling a bit. It's always an awesome and amazing and special thing to see. It's the launch day. It's a little windy out here today. It's a beautiful day. It's a little windy. It's got me concerned. My launch intuition is tingling a bit. I grew up here in Florida. I came to this very spot out here in the Causeway as a kid. My dad would take us to launches all the time. So personally, it's like the kid in me comes out when I come here. It's really cool. I've been on both sides of it. I've been a researcher, and then I've been now helping researchers. And I got to say, it's nervous on both sides. You have a lot of worry, I guess, as a scientist. You have a lot of work involved. As a payload provider, you hope you've checked all the boxes and you've done all that you can do to make everything work for the researcher so that they get good data. It's not easy to put even the most simplest payloads on the space station, but it's worth it. It's worth all the work. I think some of the biggest discoveries we've made and are going to find are up on the space station. It's incredibly important.
Well, we've been really nervous all the way up until right this moment. Nervous that our dreams aren't actually going to happen. But now that the larger countdown is happening and the rocket's all fueled up and everything looks like it's going to happen on time, it's getting really exciting. The last 15-minute window before it takes off. thanks to Cases for funding this, thanks to NanoRacks for helping us coordinate and making the hardware and coordinating all the data collection too. And thank you for the astronauts who are going to be working on this project on station. So a lot of people worked on this. It's not just the two of us. It's been a lot of people. So we really appreciate all their support.
7, 6, 5, 4, 3, 2, 1, 0. And liftoff.
As Falcon 9 and Cargo Dragon take flight, bound for the International Space Station with fresh supplies and research, helping to maintain our human presence in space as the station celebrates its 20th anniversary.
It'd be incredible just to watch it no matter what, but knowing that we have a personal investment in it makes a big difference.
Yeah, so it's just knowing that something that we've been working on is on it, and then watching the whole experience makes it just different. It really, I can't find the right words to explain it. Really,
Definitely feel like the work leading up to it was worthwhile.
yeah, absolutely. And watching it with your best friend,
Yeah.
and like someone that you've been working with for such a long time, and it's just, I think it couldn't get better. That's what I can say. Yeah. I didn't want to do it with anyone else.
Yeah, that is the exact same sentiment that I have too. So it was really special that we could both be here.
Yeah.
And watch it together.
Our scientist experiment is officially on its way to the International Space Station. The SpaceX Dragon capsule that gives the research its ride to low Earth orbit now must make the last leg of its journey to the hands of the astronauts in microgravity.
What's neat for us is we've got cargo vehicles coming and going to the ISS all the time. It is really like a busy parking lot. Vehicles come in, they stay for a few months, we do a whole bunch of science, and then they leave again. And before you know it, the next one's coming up. Now, what's important to remember is that these vehicles cannot dock themselves to the space station. We have to bring them into the space station utilizing robotics. And what I like to tell people is performing robotics, going out and capturing that vehicle is like a really difficult video game. And so we practice over and over and over again using computer simulations on how to actually capture that cargo vehicle to bring it into station. Once that cargo vehicle docks to station, we do a series of pressure checks and equalize that pressure with the International Space Station, and finally we get to open the hatch. Very quickly the crew starts to move because we've got some experiments that are actually kept at certain temperatures, and we have to transfer them quickly out and keep them at the same temperature there on board the space station.
Elaine and Peristu's research is one of the experiments that requires quick unloading. Stored at a constant temperature to ensure the hydrogels stay intact, it's one of the first items that astronauts must remove from Dragon. Then, with the experiment finally aboard the space station, it's time to conduct science in microgravity.
This was fantastic for me. This is what I do. This means a lot to me as a clinician. And so it was really neat to be able to perform that sort of science on station.
So station 1002 is loaded.
Choose your lettuce leaf. Cheers. Cheers. We get balls over? Oh, that's pretty good.
Wow.
It's a salad. It's a salad. JC, that was delicious.
Just be all Serena, that sounds great.
Well, when you haven't had a salad in 6 months, it's delicious.
Still station on 2 for Nanoracks.
With you on 2 for Nanoracks.
Right, how's your view? Do you want anything different?
View looks great.
No, the view looks great, thank you.
Now that the experiment is aboard the space station, it's time for the astronauts to get to work. Elaine and Paris Stu are back in Virginia, and the Nanoracks team is back in Texas, where they will perform a ground control version of the experiment being conducted by the crew in space.
The crew members are using the Nanoracks plate reader to read the plates. They're analyzing what's in the plate and the migration of fluids between the 2 chambers that are on the plates. And so we have our ground samples here. These are identical to the ones that are on the space station. And what we're going to do is, as the crew members insert the plates into the plate reader on the space station, we're also going to insert the plates onto the ground unit we have behind me. And that's just to confirm that what we're seeing, any effects that we do end up seeing, is effective the space environment compared to the ground unit. In summary, what the plate reader does is, it's called, the big fancy word is a spectrophotometer. And it's got a big lamp in it that shines white light, and then it's got a prism or a grating. And the white light shines on the grating, and then it moves to orientate to kind of separate the light into a wavelength. And you get to select which wavelength you want to shine through your samples. We have 6 plates. Each plate takes about 4 minutes, so it's about 30 minutes each. And every time in between, we'll be listening for the crew member to say that they inserted the plate. Then we'll hit the command here. Once the run is done, the crew member will come over and take the plate out, put the new plate in, and it'll repeat for 5 more times.
Still station on 3, plate 1003 is in the tray.
Oh yeah, it's reading the plate. It's got a little, the plate sits in there, moves the plate this way, and then the read head moves this way. And a little here, that's kind of the lamp that's in there that turns the lamp on. Sounds like bad techno music.
My crewmate actually was the first one to start this experiment, and I took over for him and said, hey, what experiment is this? What are we doing? And he looks at me and he says, I'm not sure. So we called down to the ground, to mission control.
And I know that part of this is we're looking at a gel that wound site, but I don't know what happened to that plate in the Nanoracks reader this morning, and then kind of what's going on this afternoon.
What we're looking for is how the drug migrates through the gel over time, which is why we're scanning the plates 2 times a day for this 2-week run.
I like that answer. That's very cool. Thank you for finding that out.
No problem.
So this is 15 days. It's twice a day, and they're typically in the middle of the night, which is the morning for the crew on space station, and then usually sometime in the late morning, early afternoon here. But Kyle's been running the show. He's been getting up every 6 hours, 8 hours, 7 hours to do this. It's kind of fun in a way. I get to play astronaut on the ground, so that's always fun.
After 15 days of running the experiment, the researchers have a lot of valuable data about how hydrogels behave in microgravity. To learn even more, the samples will come back to Earth for further analysis. For the last leg of their journey, the samples will return to Earth in the same Dragon capsule that gave them a ride to microgravity. After Dragon splashes down in the Pacific Ocean, it's taken to the port of Long Beach, where NASA will be ready to retrieve the precious cargo.
Splashdown for Dragon was on Sunday, I believe. And so NASA has a group called Cold Stowage and Cargo Manifest, and they go out and pick up the payloads from Dragon. And then they distribute it to people at LA or whoever needs them there, and then they bring them also here to Johnson Space Center. And so now I'm out front at the Cold Stow office, and I just picked up Module 74, which is our Tympanogen project. And they hand it to me, and I put it in my cooler, and then I drive it over to our office, where it's going to sit until we fly up to the Tympanogen office in Richmond, Virginia, to do the final phase of the experiment, which is removing the samples out of the reactor microplates. We're really proud to take part in this really interesting experiment.
When we first got our gels back, it was already exciting because space never loses its cool, and so we had these places where, oh my god, these are what the astronauts touched. And so we opened up and they've been to space and back, and now they're in our lab.
Nozzle swing. There we go. Fuel flow. Get ignition. This is really good for the tank. I'm going to go to a lot of irritation and my complete. 1.9 altitude.
Here we go. 3, 2, 1, release.
Still got it. Awesome.
I'm gonna hold level for a minute here. Say 3-6, we're gonna hold here.
Flight controls to G look good? 2Gs, copy.
Whenever a NASA aircraft leaves the ground, an entire team of people ensure that it executes its mission safely and successfully. The pilot and mission controller sit at the ends of a complex stream of data, along which dozens of IT specialists, engineers, and technicians work to ensure that each in-flight decision is informed by accurate information, and that all test or science data is successfully gathered and processed. At the Armstrong Flight Research Center, this team makes up the Mission Information and Test Systems Directorate, known simply as Code M, a critical behind-the-scenes force that helps Armstrong keep its reputation as one of the world's finest flight research centers. In most cases, new flight projects first approach the Mission Integration Office, or MIO. The MIO is responsible for the development of partnerships with key researchers, mission directorates, and external stakeholders. They help create value for our partners by providing an initial interface and a cross-functional integration of processes, capabilities, and operations.
And there's 10,000 feet.
I'm going to go about 100 feet above you if I can, yeah.
Okay.
Flights of new aircraft or systems are first simulated to ensure that any novel concepts are working as designed, or to conduct trade studies, or to iterate a design towards optimum performance. Later, when an actual flight is scheduled, before the aircraft even revs its engines, simulation familiarizes the pilot and mission control team with the procedures and test points, and prepares them for unexpected situations. Engineers and technicians in Code ME, the simulation engineering branch of Code M, create one-of-a-kind simulation programs and hardware subsystem interfaces that enable NASA's pilots and their industry partners to understand how a new aircraft or system will handle, or discover the most efficient ways to hit their data points.
Paul, I'm going to light the burners just for a second here, just see the difference in the thrust.
All right.
And,
so the cable tension go up a little now, it's into the red.
All right, coming out of the afterburners, back to full power. There's some slack.
Yeah, there's some slack on the rope now.
Oh yeah, it's amazing now that I'm getting kind of used to the sim. I can really feel you back there and the effects.
That would make sense.
Ready to send checks.
Sending check command now.
Send arm.
Arming now.
Ready to send terminate.
And terminating now. And we have a good arm term cycle.
Well before the research flight phase, the Range Engineering Branch, Code MC, engineers and software developers build, integrate, and verify range assets. This is how they ensure the aircraft telemetry can be received and processed for control room display monitoring. That aircraft position can be tracked for situational awareness.
All right, this is TD on data 2. Go ahead and check everybody for their control room display status now that we have both engines up.
Heard you loud and clear.
And that control room voice communications are working. For unmanned aircraft, Code MC verifies uplinks for command and control and flight termination systems.
We're going to arm and terminate.
Slaving's routed for Guy. We're high.
Got him.
Brake release.
And the squawk is a little off if you have to use it by about 5 degrees. Don't know.
Tracking the aircraft while it's in flight is the responsibility of MR, the Range Operations Branch. From working with the U.S. Air Force, which controls Edwards airspace, to scheduling flights, to keeping radar dishes locked on a supersonic airplane, to tracking that airplane with long-range optics, Code MR is responsible for getting the data from the airplane to the ground. This branch operates the telemetry tracking systems, space positioning systems, audio communication systems, video systems, mission control center, and mobile systems. After a flight, the data arrives at the Information Services Branch, or Code MI, which provides information technology solutions for NASA's workforce, everything from desktops to internet connections. Code MI also manages Armstrong's data center and network infrastructure, ensuring the right data is available to the appropriate users, from routine email to specialized mission-specific flight data. Finally, MI provides multimedia services, from graphic artists, photographers, and videographers to web and repro. These skilled individuals ensure effective communication of the many activities and accomplishments of the center. These services include airborne photography and videography, specialty services driven by the demands of flight research. The multimedia products help make this information accessible to engineers, researchers, partners, and stakeholders around the center, around the agency, and out in the public. A strong team with an important role. The Mission Information and Test Systems Directorate helps separate the real from the imagined through flight.
You know, there's this big unknown. You're headed out into this alien landscape that's just completely hostile to you. And, you know, if you didn't have a nice ship and extremely warm clothes, you probably wouldn't be able to survive. And so Mosaic as a whole, it's a year-long drifting expedition. So it involves people from 20 different nations, about 600 scientists. It's a huge, massive effort meant to study the Arctic as a system, not just the ice, but things like the atmosphere, the ocean, biogeochemistry, all kinds of things in a way that allows us to look at what's happening throughout the course of the year. So we left Tromsø on September 20th. Took us 10 days or so between leaving port, sailing out, picking up some instrumentation, and then starting to sail into the ice pack and starting to search for the flow. It was really difficult to find the flow because we needed ice that was thick enough to support all our equipment. Some of it's very heavy, and to do this safely. And actually, one of the big surprises to me and a lot of people on board was just how thin the ice was. You'd get out on the ice, but it's dangerous. It's an alien landscape. It's cold, there's bears. The polar bear situation was really interesting, yeah, and kind of terrifying. When we were out on the ice and we were setting things up, taking measurements, the bears did come back 2 times when I was there. And they came to our camp and they were doing things like messing with the equipment and going through our site. So there it was different because they're more on the turf that we had set up. You know, this is our turf now, and now they're coming in, and I could see them in places that I had been. So we were very isolated on the polar stern, and we had very limited connectivity. We had an email account we could send 50 kilobytes a message. It was a big change for me and a lot of people said, you know, after a week or so, I didn't miss it anymore. And I was one of those people. I really appreciated being a bit more isolated for a while and experiencing life in a different way. Doing field work like this brought me right there to the ice. When I do my research, I use data like this from the data that's taken up close on the ice. Sometimes that's the only way to get information on the ice. Things like how dense is the ice or how dense is the snow. You can't do this remotely. But we can use this to do calibration and validation of ICET2 over the course of the year. So this is valuable for improving the retrieval techniques that we use for ICET2. For me to be on the ground and get that different look at the ice and the surface, it just helps me as a scientist come up with new ideas and to inspire me to use the data that I have and then think about this in a totally new way, in a different way.
Rock, report range status. Range green.
T-minus 5, 4, 3, 2, 1. Go for main engine start. 0 and lift off.
This is no ordinary aircraft, and on board is no ordinary spacecraft. This C5 Super Galaxy is hauling something special.
It can carry what no other airplane can carry in the Air Force. Width, length, weight, you name it, it can get on that thing. This jet can do it like no other jet.
After 2 years of construction at Lockheed Martin in Denver and a few hours in the air, NOAA's GOES-S has finally made it to Kennedy Space Center, where the countdown to T0 begins.
It's always exciting to bring a satellite down to Kennedy Space Center and participate in that whole activity of getting a satellite ready for launch.
Getting it out here and rolling it into the launch processing facility, that was a very big deal for us. It's one of the hugest milestones in any spacecraft program is ship. It's not easy to transport something like this across the country.
And this is where the rubber meets the road. This is where all these people that have worked on this program for a couple of years, it culminates into the excitement of getting ready for what we call launch fever.
And so now, we get to kind of do some of the fun stuff, like put it on a giant airplane and take it to Kennedy Space Center, where we get to prepare it to go onto an Atlas V launch vehicle and launch.
It's the job of NASA's Launch Services Program to get GOES-S into orbit, and they have just a few months to do the final launch preps and inspections before T0 arrives. This is no easy task with a spacecraft of this size and complexity. In spaceflight, there are no second chances. A successful launch is resting on their shoulders. It has to be perfect the first time.
It's very exciting. I love being a part of this, and I love being able to contribute to the spacecraft and to its success.
GOES-S is the second part of a weather satellite upgrade project NOAA is undertaking, destined to save lives by modernizing our weather forecasting ability.
We have a very young team, and this will be their first campaign. So we're trying to put the excitement into that, let them feel what it's like to touch the spacecraft for the last time. Launch operations is time we all get together for one goal, which is launch.
But achieving that goal will not be easy. The road to T0 has just begun. There's only one cargo ship designed to transport rockets for United Launch Alliance. And tonight, it's pulling into Port Canaveral with the robust flight hardware of an Atlas V.
We're a high-tech vessel, high maneuverability. We have to be because we get into some tight areas on shallow rivers. The Delta Mariner is unique. It has 2 aft Z drives coupled by computer with the bow thrusters that turns 360 degrees on demand.
This crew has work to do. In less than 4 weeks, the rocket must be safely delivered, inspected, and assembled in order to successfully launch NOAA's highly advanced GOES-S weather satellite.
I sense from the crew the pride being part of this mission. And when I put this vessel alongside the dock, it is a very accomplished feeling that we all have.
The arrival of the Mariner is the start of operations for the flow of a rocket.
Teams from ULA and NASA's Launch Services Program start by unchaining the Atlas V booster and Centaur components, wasting no time in developing a plan and getting organized for transport.
We're going to take the booster over to the ASOC. It's going to be Convoy 1, it's going to be the leader, followed by the booster.
It's a very exciting day for the vehicle system engineers as we're offloading the launch vehicle that will carry the GOES-S satellite.
Here comes the Centaur second stage, with its pressurized stainless steel tank as thin as a dime. Unable to support its own weight until fully fueled, it's carried off the ship by a specialized trailer. Next comes the Atlas V booster, all 106 feet of it. This booster and 4 solid rocket motors have one job: provide enough energy at liftoff for the entire launch vehicle and payload to overcome the pull of Earth's gravity.
I never get tired of seeing the rockets come in. It's very exciting, especially on the Mariner.
Now on land, a challenging cross-base transport lies ahead to the Atlas Spaceflight Operations Center. Inside this multifunctional facility, crews will remove the protective coverings, inspect the hardware, and install the final flight components. For now, this mission remains a go, but the highly complex job of stacking the rocket is still to come. Dark 30, Cape Canaveral Air Force Station. With a full week of intense rocket assembly activities ahead, the teams from Launch Services Program and United Launch Alliance are getting an early start. It all begins with the booster. The booster is the backbone of the Atlas V, and literally everything is riding on it. It's the largest component and first to be lifted.
The Launch Services Program partnered with United Launch Alliance to select the Atlas 541 vehicle because it is one awesome rocket, and we need that thrust to get GOES-S to its geostationary orbit to meet its mission requirement.
It will take more than just the booster to get all the way to geostationary orbit. That's why we're adding 4 solid rocket boosters.
When you start with the Atlas booster, it's like 860,000 pounds of thrust with just the RD-180. So we need the solids for extra performance. We need it to get heavy payloads off the pad and for additional performance going to geosynchronous orbit or geotransfer. Mating the solids to the booster is a very hazardous operation. We have safety with us at all times. You have 100,000 pounds going up into the air and hanging on a crane. And oh, by the way, it's explosive.
Once the solids are mounted, it's time to mate the Centaur.
The Centaur is the upper stage, and it's tuned. It's like a highly tuned race car. It's light, it's efficient, it performs well for us.
We're out here to do the job and get it done right. If you see something that's not right, bring it up to us. Let's give us a chance to fix it, okay? All right, girls, get in position to do this thing.
Assembling a rocket can make or break any mission. It takes tremendous coordination and skill to get this job done. The team makes it look easy, but rocket science never is.
The coolest part of my job is coming down here and seeing the hardware and knowing what it's capable of. We all get to work with rockets, and it's really exciting and fun, and everybody has their part in all of that. And yeah, when you're out with friends, you can say you're a rocket scientist. I do.
So there's really nothing quite like all the work and all the setup that we do to get ready to do this and get built up a rocket and tested to get to launch day. And when we get to T0 and the rocket lifts off and the control room rattles and shakes a little bit, it's an awesome feeling. That is the ultimate reward, and that's really what makes us happy, what makes our customer happy, is putting our customer where they want to go in the right spot, in the exact right orbit. And that is, there's a lot of pride in that.
This rocket is almost ready to roll. Of course, the only thing missing is its GOES-S payload. 2 weeks to T0. Today is another huge milestone for NOAA's GOES-S mission.
So today we start something called encapsulation. By encapsulation, we actually put a container around the satellite. It's called a payload fairing. That payload fairing will protect the satellite for the first 3.5 minutes of its mission. It sounds like a very short period of time, but in fact, that's when we would have the maximum aerodynamic and acoustic loads on the satellite. So we're trying to protect the satellite. Right now, we really have tested everything we need to do to make sure this satellite is ready for launch. The next time we'll see this satellite is on orbit.
Shooting off the launch pad like a bullet, this vehicle will rocket past the speed of sound in just over 30 seconds. If not protected, the Earth's atmosphere will rip GOES-S to pieces. But for a satellite designed only to live in the vacuum of space, life on Earth can be just as dangerous. Any exposure to dust or moisture could contaminate the satellite and destroy the mission. That's why this fairing is more than just a suit of armor. It's also a portable clean room. With encapsulation complete, it's time to call in the KMAG. This 72-wheel transport vehicle is what it takes to get this massive payload to the pad.
Spacecraft hoist and mate to the launch vehicle today is a huge milestone for the whole operation. And this is the biggest integrated operation that we've had so far. And it goes all day, goes all night, from transport and then hoist and mate, and it'll go into the evening tonight as they finish closeouts.
After working through the night, LSP and ULA are almost there. Just 150 feet to go, straight up.
Obstacles, we do have obstacles on the decks, on the KMAG, so watch your step, walking area, trip hazards, and then remember about your hard hats, chin straps. Any other questions? All right, let's go do this.
There's a lot of moving parts involved with processing a spacecraft, processing a rocket, and then bringing them together for a launch. There are a lot of people involved, and there are a lot of moving parts. We have a lot of hard timelines that we have to meet and deadlines that we have to meet, and everybody works as hard as they can to meet those deadlines, and sometimes we have to work around the clock to meet those.
We've reached a critical point on the road to T0. GOES-S is now mated to the Atlas V.
We've been working for several years integrating this thing and completed that now. We've got the satellite on top and we're ready to go.
With all major milestones complete, this rocket is ready to roll.
Engineer, proceed with MLP transport to pad.
Roger.
It's go time. The GOES-S launch window opens tomorrow. ULA and LSP have one last critical procedure to complete. Get the entire Atlas V stack and its mobile launch platform to the pad.
It is a fairly challenging activity if you think about moving a 1.5 million pound mobile launch platform and vehicle out to the pad.
Once it gets there, it will be loaded with rocket fuel and be ready to start the terminal count to T0. Years of intense planning and coordination are finally rolling to the pad, and the majesty of the Atlas V is on display as it inches its way to liftoff.
The thrill of seeing that Atlas vehicle, all 197 feet of it, rolling up to the pad, it's just really exciting because I know that means tomorrow is launch.
GOES-S is particularly important because of how it's transforming our capability to predict weather and protect lives and property. And I can't wait for it to launch tomorrow and become operational.
So great to be here after a number of years of seeing the spacecraft come together and all the instruments integrated onto the spacecraft. Our baby is tucked in and ready for launch tomorrow.
This is the LC on 1 performing pre-test briefing. This operation is classified hazardous. Cryogenics will be loaded. ALC verified count to start at 1947 Zulu. Verified. Proceeding with the count.
We're launching today, and the ULA team got on console a few hours ago,
turn power on the rocket, and we are counting down to T0 right now. I'm on my way over to the ASOC, the Atlas Space Flight Operations Center, where the Mission Director Center and the Launch Control Center are located. And if the range is clear and the rocket is good, we're go for today. I love launch day. I'm so fortunate to work with a great team. Our team gets so incredibly excited to do missions, and it all culminates today.
Range coordinator. Clear to proceed. Launch director, you have permission to launch. Proceeding with the count. ALC verified T0 is set for 2202 Zulu. Verified. Rock report range status. Range green. Status check. Go Atlas. Go Centaur.
Range Operations Controller reports range green. Everything is go.
7, 6, 5, 4, 3, 2, 1. And liftoff of Atlas V and NOAA's GOES, a highly sophisticated weather watching eye in the sky to join its twin in providing better forecasts and saving lives.
Atlas has begun a pitch and yaw maneuver to steer to its planned path, an azimuth of 100.7 degrees.
It's just a thrill, especially when it all ends in launch success and mission success for GOES and this cutting-edge weather capability that our nation will now have.
There's one thing that stands between us and the harsh environment of space, our atmosphere, the part of Earth that sustains all life. But here, in the closest town to the North Pole, it's slowly leaking away. A team headed there to launch rockets into the leak, but it's not the lack of atmosphere that they're concerned about. The leak is a natural process that will take billions of years, so we're not going to run out anytime soon. It's part of the larger story of how a planet's atmosphere changes over time, a key factor in the search for life on other planets.
We have 35 residents and 60 of our team together in a town that is completely isolated. There's a plane twice a week, and there's 1,000 polar bears nearby.
This is Doug Rowland, a NASA scientist who's taken his team to Ny-Ålesund on the island of Svalbard. The island lies beneath one of two regions near Earth's poles called the cusps. It's where we can access space directly, and where 100 tons of atmosphere escapes into space each day. This escape gives clues to how long an atmosphere will last, and ultimately, whether it stays around long enough to sustain life.
What we're trying to understand is how did Earth's atmosphere evolve over time? And how do other planets that might be like Earth or more dissimilar to Earth, how did their atmospheres evolve?
So Doug joined forces with Göran Moen, a professor at the University of Oslo, who started the Grand Challenge Initiative CUSP. It's an international mission to launch 12 rockets into the Earth's northern cusp. And Doug, he's the mission leader for the first 2 rockets of the campaign.
We don't want to waste our rocket. So it took us 3 years to make the rocket and only 15 minutes to use it, and I don't want to waste my shot here.
He's using a sounding rocket, which is different from the bigger rockets that carry satellites and humans into space. It's a small suborbital rocket that flies briefly into space, collects real-time data for around 15 minutes, then falls back to Earth. It's affordable, quick to build, and can launch towards a precise point.
The major advantage is that you can launch into a target on the sky.
But there's a limited launch window and only one chance to get the launch right.
We have these unguided rockets. They go where you point them, unless the wind is blowing, because the wind literally just blows them over. We don't launch when there's high wind.
So to measure the winds, they launch balloons with GPS trackers. They're released every 15 to 30 minutes, and then they're monitored to see how fast the winds are carrying them.
The ground winds were 12, 13 meters per second, gusting 17, which is way off.
You're filled with trepidation. Oh my gosh, this thing that I built, is it going to work after all this?
So
So I think we're going to scrub for today. I'd like to thank everyone. I think it was a great performance. Thanks a lot.
This means that we are scrubbing this operation for today and we'll try again tomorrow.
The mission is named Visualizing Ion Outflow via Neutral Atom Sensing 2, or VISIONS 2. In short, they're looking at how oxygen is getting enough energy to escape.
It's a good test of how atmospheric escape works. Earth's gravity should hold onto the oxygen, and yet we see this gas shooting off into space. We're trying to figure out how that works.
That is a science question that has been hanging around for 4 decades.
Fortunately, anyone can see atmospheric escape at the right place and time.
In Svalbard, we have the so-called polar night. It's dark all 24 hours.
Its continual darkness is key for witnessing this. This is the cusp aurora. It's a type of northern lights that appears between 8 a.m. and noon, and you can only see it when it's dark during the day. It looks similar to the aurora that occurs at night, but when these iridescent colors dance at this hour each day, 100 tons of oxygen escapes from Earth's atmosphere into space.
This is our sport now to chase the aurora.
Working with them is the ISCAT radar and Kjell Henriksen Observatory. They have additional instruments to find the aurora.
Sometimes it's cloudy, so we use radars to track the cusp.
We can give advice that this is the right type of aurora.
This is the Wall of Science, a collection of data from satellites and ground instruments that helps them predict where the cusp aurora will be.
So the cusp actually isn't a fixed point in space, it kind of moves around.
What's controlling the cusp's movement is the sun interacting with Earth. Our planet is surrounded by a magnetic field that helps us hold on to our atmosphere. But at the north and south poles, the magnetic field bends inwards, creating a corridor between Earth and space.
When energy is released from the sun via a solar flare or coronal mass ejection, all of that energy in the form of radiation rides down the magnetic field lines of the Earth and is transferred and dumped into the Earth's atmosphere.
Electrons cascade into Earth's atmosphere. They accelerate and collide with oxygen particles, giving them energy to release light and sometimes enough energy to escape. Collectively, this forms the cusp aurora and streams of escaping oxygen.
This cusp is in constant motion.
And we've got a fixed trajectory. We really can't aim at where the cusp is. We have to wait for the cusp to come across our line of sight.
Can you guys hear Kjell?
We'd like you, as soon as you see an indication the cusp is moving close, to move it, the radar dish if we can.
This is ISCAT. It's been very quiet, very difficult to launch.
Do you think we're going to launch today?
No. Probably about a 60% chance of launching.
When we started seeing this really good data, this clock started counting down, and that's when everyone realized this is going to happen. We're going to launch.
We're doing everything we can to get that launch off before the aurora goes away. It is really, really challenging and nerve-wracking at that point. You can see the tension just rise in everybody when that happens.
And so everyone's watching their instruments, getting really excited, and then at T-minus 1 minute, all of us ran out to go see the launch happen. And then we immediately turned around and ran right back in to look at all the data that was coming back from the instruments. You know how much time and effort went into it because we all worked on it, and there's just nothing that compares to that feeling.
Everybody in every one of those little places, really just so happy to contribute to getting this science. It's really an incredible experience.
This is a story about what it takes to launch science instruments into space, but the real adventure will be in the data they sent back. Hidden within the numbers will be answers that reach far beyond Earth, shedding light on how atmospheres throughout the universe change, evolve, and perhaps support life.
Orion is getting ready to launch. My name is Kelly Smith, and I work on navigation and guidance for Orion. Orion is NASA's next-generation spacecraft. Built with versatility in mind, it can take astronauts deeper into space than we've ever gone before, to an asteroid or even onto Mars. For these missions, Orion has to be one tough spacecraft, withstanding high speeds, searing temperatures, and extreme radiation. Before we can send astronauts into space on Orion, we have to test all of its systems. And there's only one way to know if we got it right: fly it in space. For Orion's first flight, no astronauts will be aboard. The spacecraft is loaded with sensors to record and measure all aspects of the flight in every detail. It all begins with launch aboard a Delta IV Heavy rocket. As it punches into Earth orbit, Orion will jettison its launch abort system. The abort system is a safety feature designed to pull Orion and its crew out of danger if there were a problem with the rocket during ascent. Orion's journey is just beginning. As the spacecraft and the upper stage begin their first lap around Earth, Mission Control in Houston is monitoring the progress of the flight. Orion's over 100 miles up and going about 17,000 miles per hour. Just as it passes over the Indian Ocean, we lose communication. This is expected. The communications link we have through satellites to Orion is momentarily lost, but Orion continues to receive and process data. Its computers can handle 480 million instructions per second. Imagine you are traveling with Orion as the flight test continues. One orbit completed. Time to go. The upper stage of the rocket fires again. Like the setup for a roller coaster ride, this is the big climb we've been waiting for. We are headed 3,600 miles above Earth. 15 times higher from the planet than the International Space Station. As we get further away from Earth, we'll pass through the Van Allen belts, an area of dangerous radiation. Radiation like this could harm the guidance systems, onboard computers, or other electronics on Orion. Naturally, we have to pass through this danger zone twice, once up and once back. But Orion has protection. Shielding will be put to the test as the vehicle cuts through the waves of radiation. Sensors aboard will record radiation levels for scientists to study. We must solve these challenges before we send people through this region of space. For this flight, it's time to head home. The upper stage of the rocket triggers separation. Orion's jets fire to turn it into the proper position to re-enter Earth's atmosphere. No matter what happens now, we're coming in. 75 miles above Earth, the spacecraft enters the atmosphere. Things happen quickly. We're now traveling more than 20,000 miles per hour. Air particles pushed out of the way heat up. An envelope of hot plasma surrounds the vehicle as it plummets towards Earth. The plasma reaches temperatures of 4,000 degrees Fahrenheit, almost twice as hot as molten lava. This may be the most dangerous part of the flight. Mission Control is monitoring all the data from the spacecraft, and then we lose communication again. No data can penetrate the plasma. Orion is on its own. Orion is inside a fireball. Onboard systems ignite jets to keep the ship pointed correctly, so the specially constructed heat shield takes the full brunt of the inferno. This is the largest heat shield of its kind ever made. Orion's computers command the spacecraft to bank like an airplane, keeping a precise path to the landing site. Even though we've slowed from 20,000 miles per hour to about 300 miles per hour, we're still traveling amazingly fast. We must slow down to safely land in the ocean. Luckily, we have parachutes. Specially designed for Orion, the parachutes help us hit the brakes, but not too quickly. One day people will be aboard, so deceleration must happen in stages to keep things comfortable for the crew. The forward bay cover jettisons. Two drogue chutes deploy and slow the returning spacecraft down to 175 miles per hour. Then, the three main parachutes open. Once fully engaged, this canopy would cover an American football field. It takes parachutes this size and strength to slow our descent to 20 miles per hour, and then splashdown. For this first flight, we won't have astronauts inside, but we still have some very precious cargo. The flight data from this mission is stored inside the Orion spacecraft. While our flight might be over, there is still a lot of work to do. Onboard sensors recorded every detail, from launch to flying in space, to re-entry to landing. Flight tests are difficult and complex, but they give us confidence that the systems we have designed work under real flight conditions. It's great to be a part of this first space flight for Orion, and we're looking forward to beginning a new chapter in human space exploration.
Welcome to NASA Edge, an inside and outside look at all things NASA. We're joined by Michelle Monk and Steve Gaddis. How you guys doing?
Great.
And we have a very important topic today, and that's going to be EDL, or Entry, Descent, and Landing. Now, Michelle, you're the principal technologist for EDL.
Yes.
What is Entry, Descent, and Landing?
Entry, descent, and landing is how we get a spacecraft from the top of an atmosphere to a planetary surface. So the entry part refers to, the atmospheric flight, most of it, and then we have descent and landing, which is usually propulsive and get us down on the surface safely. We do D and L at places that don't have atmospheres like the moon or, asteroids, but usually we talk about EDL when we talk about atmospheres.
So Michelle, what is your role as principal technologist for EDL?
I look across all the missions that NASA has coming up that will use entry, descent, and landing on any planet, and I look at the technologies we're going to need for those missions, and I bring them forward to the mission directorate for starting funding.
So you have a need in the EDL world, in the community. You're coming up with the technologies that are needed for future missions.
Right.
So you take some of those technologies that maybe are less mature, hand them off to you.
Right.
And then you mature those technologies.
Design, develop, test, and evaluate.
Is that a pretty easy task, trying to figure out
Not at all.
what technology you're going to need?
Not at all. I have to look at both the human missions that are coming up, so, sending humans to Mars.
Right.
I have to look at the scientific missions that are coming up and all the destinations the scientists want to go to, and I have to kind of rank those and prioritize them and figure out, where they are in terms of maturity and what the best infusion point will be. When is the first mission that can use that technology? And then I have to figure out what is the best program within STMD for the investment. Is it better to have a university work on it, or a small business, or is it better for a game-changing program element?
And your job is really hard, because we're going to be talking about a suite of EDL projects over the next two shows, because there's so much content in EDL.
There's a lot of
We can't
content.
do this into one show.
Absolutely.
So this will be part one of two parts. So how do you manage all that?
Well, one is it's hard, but it's also fun. Okay. And we've got excellent technologists leading every one of these activities, so we all work together. And we all know that we need these technologies, so we're motivated to see them be successful.
We're a very passionate community.
Yes.
I've seen it in all the interviews that we've done. You guys are definitely passionate. Now, the first one that we're going to be talking about is ESM, or Entry Systems Modeling. What is that about?
So that's the first part of it, where they develop these models and simulations to understand how the technology works and how it will be beneficial at a system level. It's very cross-cutting against all the projects, and the plan is to take that data and then infuse it into the projects.
Blair had a chance to go out to NASA Ames Research Center to talk to Mike Barnhart, who is the Integrated EDL Systems Lead. Let's check it out.
Mike, tell me a little bit about Entry Systems Modeling Project. What is it?
So the Entry Systems Modeling Project is tasked with developing a lot of these technologies that are coming from lower technology readiness level, things like academia, and trying to bring them up to a level so that we're ready to help them.
So in this particular situation, we're talking about EDL projects, and so you're actually helping them raise their technology readiness level?
That's right. So any of these things, Orion, Mars 2020, Mars Insight, anybody that's flying anywhere in the solar system and they need to enter an atmosphere, you have to go through an entry, descent, and landing phase. And we don't have all those problems solved. We don't have all those technologies built. And so we're continually trying to improve on our existing technologies and also renew with new ideas. And that's the real purpose of the Entry Systems Modeling Project.
How do we get the data we need to improve the EDL process across these missions?
Right, so there's a lot of different things that we can do. We have ground facilities, which we rely on a lot. So we have arc jets that we do for material characterization and developing models for material response. We have our shock tubes, which we use to develop radiation models. We have wind tunnels that we use to build aerodynamic models, the dynamic motion of a body as it's flying, that sort of thing. We need to know all that in order to have a successful entry into a planetary atmosphere. So that's the simplest thing that we have access to every day. And then we also have, some amount of flight data. So there was the Orion EFT-1 flight last year, which was very successful, and we can use that to take our models and look at our predictions and then try and back out, exactly how well are we doing, quantify, how well are we predicting that.
You've used a lot of data from the Apollo era. Are you able to use data from things like MSL and more recent missions to help? Because I know we have limited data on entry.
Yeah, so MSL is a really great example because we flew Medley on MSL, and that allowed us to get some of the only data that we've had on entry at Mars. So heating data, pressure data, which we use to reconstruct the aerodynamics, is fantastic tool for us, but there's a lot of challenges there as well. So it's really, it takes a village. You need to have your computational models because they're the only thing that's going to access the true flight space that we have here on the ground. We have ground facilities that simulate parts of the flight space, and then ultimately you have a little bit of flight data. And your goal is ground to flight traceability. Let's predict what we do on the ground. Let's predict what we do in the air. And let's see, how far apart are we so that we can quantify when we're designing the next mission exactly where we think we'll be.
Are you sharing that data with all the different EDL potential systems that are being developed?
Absolutely, absolutely. Everything that we do in the Entry Systems Modeling Project is, for the greater good. We work very closely with academia. So we've got university partners that we are sharing this data with to help improve our models. We share it with other projects. So with radiation modeling, we were working very closely with the INSPA project and OSIRIS-REx projects because they had issues with radiative heating on their back shell. So they call us because we're the radiation modeling experts, and they say, here's our problem, tell us, how worried do we need to be?
Be worried, be very worried.
Yeah, we're always looking to help everyone else around the agency, and that's really what Space Technology Mission Director is all about, right? Is trying to help the other directorates with the technology that they're going to need.
Tell you what, great interview with Mike Barnhart. I mean, it really kind of gives you the flavor of how difficult EDL really is.
Right.
I mean, if you can't characterize it and model it here on the ground, I mean, you'll never be able to land.
That's right.
And you can't test an entry system on the ground and get the flight-like data that you need to design.
And that's the challenge but with Medley on MSL, that was a game changer, wasn't it?
Absolutely.
I mean, you actually, for the first time, were able to actually see the health of the spacecraft as it was entering the atmosphere.
Yeah. Right. As engineers, it's great that we succeeded, but I want to know if I got an A+ or a C- on the design. So the Medley data allowed us to actually know how we designed the vehicle.
And based on that Medley data, what were the results? They were pretty good, weren't they?
They were fantastic. But we found some things that we didn't know. Radiative heating is important at Mars and at the scale of MSL. We didn't recognize that before.
And now, since it was such an important mission for you guys, now you're going to take it to the next level for Medley 2 for Mars 2020.
For Mars 2020, yeah, we've got that going, and they're right in the middle of their preliminary design phase. Right. They're all excited. They're going to put some new measurements on the back shell.
Yeah, they were actually at Aberdeen Proving Ground last week doing some testing to see where to put the pressure measurement on the back of the vehicle. Right. So yeah, it's really exciting to get this new data in the back shell and using new sensors.
We know Blair had a chance to sit down with Mark Schonenberger, who's the reconstruction lead, which I got to ask you about that when we come back, because I never heard of a reconstruction lead. But we're going to learn more about Medley 2. Let's check it out.
So Mark, when we think about the differences between Medley 1 and Medley 2, it's interesting because Medley 1, the M stood for MSL, Mars Science Laboratory. Now it's Mars 2020. You guys caught a break. You get to use the same letter.
We still get to use the same letter. I think it'll just be shortened to Mars, EDL instrumentation, and it'll hopefully continue for a bunch more Medleys, Medley 3, 4. We can always call it Mars.
Perfect. It's a nice little series you got going.
We're getting great data. So.
Now I'm wondering though, in terms of technology and in terms of how you're growing Medley, I mean, Medley 1 was a very successful mission as far as the data we got back. What are we expecting for Medley 2?
For Medley 2, it's really to dig in and look at the pieces that we couldn't quite get for Medley 1. The instrumentation there was it was the first time we'd flown instrumentation since Viking to get pressure and heating data. So we really tried to capture the whole event. And to do that, especially for pressures, we had these transducers that could see the peak high pressure as you went through the hypersonic phase, and you're really slowing down around Mach 18. And then as you slow down, you really start getting in the noise there with the kind of information you can get. The signal was just really weak. It's sort of like using your bathroom scale to measure the ingredients for a cake. It's just, there's not a lot of resolution there. So it's tough. You don't really trust those measurements.
That's about how my cakes turn out, as if I measured ingredients with it.
So what we did here now is to use more of a postal scale for pressure. So we're measuring down at the low range when we're flying supersonically. Right as we get near parachute deploy, we're spending a lot of time just kind of slowing down, flying at the same altitude, but you're really at terminal velocity. You're not slowing down real well.
Now, is that pretty much in the part of the descent, if you will, that where you've burned away most of the heat shield that you're going to in the process?
Yeah, all the heating's over. I mean, it's still a little warm and things are kind of winding down, but yeah, all the exciting heating stuff is over, and you're really just trying to bleed off energy until you get down to a condition that's safe for the parachute. And so any error in your prediction of how that vehicle slows down, or your prediction of what the atmosphere is going to end up being on the day at Mars, can lead to being far uprange or far downrange. Your landing ellipse and how you target it, you need to account for that. So if we can get better data to characterize the aerodynamics, we can tighten that up and land in even smaller spaces.
Which is always the goal, right?
Yep.
You're trying to find out exactly where you need to land.
Yep.
So Mark, how is the instrumentation different on Medley 2 from Medley 1?
So, at least from my experiences with the pressure side, Medley 1 was really designed to capture the pressure all the way through entry. So it had this nice high maximum pressure it could measure. What we really wanted to do for Medley 2 was to look for the low pressures right before chute deploy. We're going to be coasting there, slowing down from, say, Mach 4 down to Mach 2 for a minute, 100 seconds, something like that. And that adds to the landing ellipse, any error in aerodynamics. So the transducers, we put more of them on the heat shield, and they're at a lower range, so they'll have much better resolution at those low speeds. So we can pull out things like winds, and we can get a better estimate of the drag. And we also have a pressure transducer on the backside. As you slow down, get down to supersonic speeds, the pressures on the back shell become a big contributor to the total forces acting on the capsule. And it's really hard to predict, actually, what those pressures are. So with some truth on the backside, that can really help us nail down the total behavior of the capsule as it's flying at those low speeds.
It seems like we're getting an awful lot of good data on the things that are happening during EDL and Mars, especially from Medley and Medley 2. Are we able to, in the future, maybe translate what you're doing here to potential different atmospheres or different EDL circumstances?
Absolutely. So Medley 1 definitely demonstrated, and it was the reason I think we have Medley 2, was it became the model of how you put an instrument package on a heat shield, how to work with the project to do it, so that they're not scared about, putting holes in their pristine heat shield that's designed to keep their rover on the ground. We have a process now to do that. So you'll see missions going to Venus or Jupiter, Titan, those kinds of things. They'll all have instrumentation during entry, and NASA has the confidence to require that because we did so well with Medley 1 and hopefully again with Medley 2.
Mark did a really nice job discussing Medley 2, but I have to ask the question, in all my years at NASA, talking to subject matter experts from all 10 centers, what is a reconstruction lead?
Reconstruction is really important after a flight to understand exactly how and where the vehicle flew.
Oh, okay.
And without the proper data, it's really hard. You have to make some assumptions.
Okay.
So for instance, before Medley, when we didn't have an independent pressure measurement, we had to assume something about the aerodynamics of the vehicle in order to figure out how it flew.
Okay.
Now with that independent pressure measurement, we can nail it and we don't have to make any assumptions. So reconstruction lead is really key to understanding how we did.
See, you learn something new every day. I had no clue.
Yeah, he comes back up with that flight plan that they had and where the data is along those flight plans. It's very important.
Now, speaking of that flight plan, with Medley 2, can you take the data from Medley 1 and kind of show what the flight plan is going to be for Mars 2020, or is that a completely different flight plan?
It's a lot the same because it's the same shape, size, vehicle. The mass will probably be a little different. They're using the same entry, descent, and landing system, but the atmosphere obviously will be a little bit different. The entry velocity will be a little bit different because of the different year.
Right.
But largely, we're going to use all of our MSL simulations as the basis for where we start on 2020.
Now, I know, Steve, with game changing, you take technologies and you take them from a technology readiness level. We always talked about that 1 through that 9 scale.
Yeah.
And you're in that middle range.
Middle range, about 3 to 5 or 6.
Right. So, but with Medley, since you have proven you have a flight underneath you, and then you're working on Medley 2, is that still considered, technology at that level?
Yeah,
it's still not space ready.
Yeah, and it was like what Michelle was telling you was we learned so much through Medley 1 that we want to put different kinds of transducers to get the lower pressure range. We want to understand the back shell pressures and radiation rates. So we learned so much, so it's not really just a repeat of Medley 1.
Yeah, we have totally new sensors. Knowing what we know from Medley 1, we've moved a lot of our sensors, so we have kind of the same number of channels of data, but we've distributed them differently on the forebody and then moved some to the back of the vehicle.
Well, speaking of a new mission, we also have now, instead of Medley 2, we also have HIAD 2.
Yep.
Absolutely.
Which is a hypersonic aerodynamic inflatable decelerator.
Inflatable aerodynamic, yes.
We did it again. It's a hypersonic inflatable aerodynamic decelerator?
Yes.
Very cool.
Bravo.
All right, so that's a completely different type of EDL system from Medley 2.
It is.
And Franklin had a chance to sit down with the project manager, Joe Del Corso.
Yes.
And we're going to learn more about HIAD 2, so let's check that out.
So Joe, we're talking about HIAD 2. Tell me what has changed since HIAD 1.
So we've had a number of changes. The first one was we upgraded our thermal protection system. In HIAD 1, we used a Generation 1 thermal protection system, which was somewhat capable. It's low temperature capable, basically something on the order of 1,000 to 1,100 degrees Celsius on the surface. For HIAD 2, what we've looked at is much higher temperature capable materials, much more flexible and lighter weight. So now we're using custom built silicon carbide materials as an outer fabric. We're using COTS materials and some custom materials for our insulator systems. And then on the backside for the gas barrier, you have woven fabric systems with PTFE film wrapped around it. Our inflatable structure is also being upgraded. And then the other thing that we're doing is we are working on scalability. We're focusing on trying to get to a 12-meter scale. In order to do that, we've got to upgrade a lot of our equipment. We've got to work on something as simple as just picking up one of the gore seams. It takes a lot of development, a lot of careful coordination. So what we're focused on is not just upgrading our materials, but also upgrading our handling techniques, our manufacturing techniques.
Tell me about the HIAD timeline from the time it was conceived to where we are right now with HIAD 2.
So HIAD has been in development, previously it wasn't known as HIAD, but it's been in development now for almost a decade, and we still have probably another 4 years worth of work to do to get us to human access to Mars. We started out in 2006 doing material testing, and really all we were doing is we were doing low-level, trying to learn how to test fabric systems so that we could simulate an atmospheric entry condition. We were learning how to learn in the early phases. We had IRVI-1 happen. Unfortunately, there was a launch vehicle anomaly, so we lost that. But what it did do is enabled us to put in place IRVI-2 flight tests. People had enough confidence in what we were doing that they allowed us to build a build-to-print. That went up on a sounding rocket launched out of Wallops, and it was an incredibly successful proof of concept. We had an inflatable structure, but no real TPS at the time, thermal protection system. Following the success of IRVI-2, we started up what we currently know as HIAD, which is the Hypersonic Inflatable Aerodynamic Decelerator project. During that project, we were doing all the lab scale development, small scale, little samples. We had learned how to do the initial testing. Now we were taking it through a maturation process, getting it ready for flight again. The third flight that we flew out of Wallops again was called IRVI-3. That was a much higher heating condition, and it was the first chance for us to actually test a thermal protection system with our inflatable structure. After the success of IRVI-3 and the closure of the initial HIAD, we attempted to fly an orbital entry flight test called THOR, the Terrestrial HIAD Orbital Reentry Flight Test. Unfortunately, due to the ORB-3 failure, we had to cancel THOR and we went back to a ground development effort. But unlike the first two ground development efforts, the third one wasn't focused on learning how to test or testing materials or developing materials. It's focused on scaling. So we did small scale in the early development phases, and now we're scaling to something more applicable for human access to Mars.
Now the cool thing I understand about HIAD 2, that you guys have a partnership with ULA?
Yeah.
Let's talk about that.
So about a year ago, ULA announced that they wanted to use HIAD technology to recover their boosters as part of their new business model, affordability. And so we've been working on a flight demonstration with them over the last year and a half.
Yeah, and that would be at the 6-meter scale, which is about halfway to what ULA would need for their full booster recovery, 12 meters that Joe talked about on the video. And it's also the right scale for us to do maybe a technology demonstration mission leading up to putting humans on Mars.
So the idea is that you're using this HIAD technology to recover the first stage of a ULA rocket. And so is that going to be recoverable, and is that going to sort of land in the ocean? Is it going to land on dry land? How is that going to work?
They actually want to snatch it out of midair with a helicopter and to minimize any refurbishment costs.
Wait a minute, so you're going to have this booster coming down with the HIAD deployable shell.
Yes.
And then a helicopter's going to come and just kind of grab it
mid-air retrieval. Yeah, it'll come in. It'll have a catch hook, and the helicopter will come. It's a modified helicopter, obviously, but that's the plan.
Yeah, we've not air snatched anything of that mass yet, so that's a little bit of technology development as well.
Wow, I seriously hope that you go back to your ESM folks and do some modeling of that snatching, because I
reconstruction of the booster trajectory.
That's perfect. Well, we're looking forward to seeing that in action, because that will be something to see when that
Absolutely.
actually happens.
That would be awesome.
And also with HIAD, which is a win-win not only for ULA, but for NASA. NASA gets a demonstration out of it, but then it kind of matures that technology to move on to an eventual test on Mars?
Yes.
Awesome. I tell you what, we've come to the close of just part one of EDL. I mean, we've covered a lot of technology today, and on the next show, we're going to be covering even more technologies.
Yeah, we should be talking about Adept and 3D Mat and heat.
And now, with regards to 3D Mat and heat, that's more of the material side as opposed to the big system side, isn't it?
Right.
I'm looking forward to that, and so stay tuned. We're going to be talking more about EDL. You're watching NASA Edge.
Our next Mars rover gets closer to launch. A comet spotted from the space station. And we're ready to build a spacecraft to explore a metal-rich asteroid. A few of the stories to tell you about this week at NASA. On Tuesday, July 7th, our Mars 2020 Perseverance rover was lifted onto the top of the Atlas V rocket that will send it towards the red planet this summer. Engineers have made physical and electrical connections between the booster and the spacecraft and are conducting the final tests before launch. Perseverance's mission: search for signs of ancient microbial life, study the planet's climate and geology, and collect samples for possible return to Earth. This mission will help pave the way for human exploration of Mars. Meanwhile, on the Martian surface, our Curiosity rover began a summer road trip of roughly a mile of steep terrain to ascend Mount Sharp. Curiosity will look for sulfates that usually form around water as it evaporates. They are a clue to how the climate and prospects for life changed nearly 3 billion years ago. Our moon exploration technologies are getting a boost from additional investments for small businesses. We've picked 4 American companies to develop technologies ranging from communications to improve driving on the lunar surface to use of lunar resources. These investments are part of our Artemis program, which aims to land the first woman and the next man on the moon in 2024. Kathy Leaders, the new leader of our human spaceflight efforts, got an up-close look at the booster segments for our Space Launch System, or SLS rocket, during a recent visit to our Kennedy Space Center in Florida. The boosters are being prepped for Artemis 1, when SLS will send an uncrewed Orion spacecraft around the moon and back. Astronauts aboard the International Space Station spotted a comet previously discovered by and named after our NEOWISE mission that studies near-Earth objects. Comet NEOWISE will pass harmlessly at 64 million miles from Earth, while giving astronomers the opportunity to learn more about its composition and structure. You can catch a glimpse of the glowing comet in the evening sky shortly after sunset on July 11th as it speeds away from the sun. Our Psyche mission to explore a metal-rich asteroid has passed a crucial mission milestone. The systems designed to do their job in deep space are now ready to be built. Psyche is planned to launch in 2022 and will fly to its target in the main asteroid belt between Mars and Jupiter. That's what's up this week at NASA. For more on these and other stories, follow us on the web at nasa.gov/TWAN.
50 years ago, we went to the moon. We called it Apollo.
What many people don't know is that Apollo had a twin.
She was a woman named Artemis, goddess of the moon.
We are returning to the moon.
As a new generation of explorers.
This time to stay.
And to prepare to achieve humanity's next giant leap of sending the first human missions to Mars.
We believe our course will redefine what is possible.
That we would discover life-saving,
earth-changing science.
And that the challenges ahead will inspire generations.
This is our manifest.
For all who wondered if we could return.
For all who dreamed of pressing beyond.
This is your calling.
We go for all of America.
We go. We go as the Artemis generation.
We go.
There's so many things that can keep the shuttle on the ground, weather being one of them. It's one of the more visible ones to the public, of course.
Weather is often the difference between go and no-go when a space shuttle is ready to lift off from NASA's Kennedy Space Center in Florida. The task of tracking the weather and determining whether or not it's safe for a shuttle to launch falls to the Launch Weather Officer. It's a service provided by the U.S. Air Force 45th Weather Squadron, based at nearby Cape Canaveral Air Force Station.
Well, it's a very tropical environment here in Florida. We have the sea breeze that occurs, we have river breezes that occur. Anytime we get some low-level convergence and we have enough moisture, we can develop showers and thunderstorms, particularly in the summertime. And so working, the weather, you want to really be able to nail it down, but there's a lot of times where there's a lot of iffy situations. And so that's where it's really challenging.
Space shuttle launches are governed by a complex set of weather rules called Launch Commit Criteria, designed to keep the shuttle and astronauts safe. There are limits for rain, lightning, clouds, and winds, and if any one of the rules is violated, that's a no-go.
It may look good out here, but we're actually could be red. And so I know a lot of people think, well, it wasn't that bad, but it's violating our launch commit criteria and we have a safety issue, so we have to call it.
The team can only begin filling the shuttle's 15-story external fuel tank if weather permits, and of course conditions must be favorable at the launch pad at liftoff. They also need good conditions for a landing in case the shuttle develops a problem during flight and must come back to land at Kennedy, an unlikely last resort emergency landing option called a return to launch site abort. Wonders relies on several forecasting tools, including radars, satellite imagery, weather balloons, and other data sources.
The location of the radar is off to the west as opposed to the south. So our new radar being off to the west allows us to pick up the sea breeze a lot better, particularly now because we have Doppler capability with this radar.
Conditions can change quickly, so the launch team often will go ahead with a countdown despite a gloomy forecast, just to be ready in case the weather changes for the better.
I recall one mission where we decided to tank and go for launch with only a 5% chance of launching that day. And indeed we launched. And so that's a case where we got lucky, probably. There have been other cases where we've had about an 80% go for launch and then we end up scrubbing for weather. More often than not, we'll give it a shot.
The team has weathered some memorable days, one of which took place in August 2006 when Hurricane Ernesto threatened Kennedy Space Center as Shuttle Atlantis waited on the launch pad.
Hurricanes and shuttle on the launch pad are incompatible, as you might imagine. And so we have very strict criteria to roll the vehicle back to the VAB in the event of a threatening hurricane.
Space Shuttle Atlantis began the long, slow roll from the launch pad to the safety of the vehicle assembly building in advance of the storm. But when the shuttle was only a third of the way through the 6-hour move, Leinbach learned Ernesto had not strengthened, and he sent the shuttle back to the launch pad.
And we went back to the pad. The storm passed about 50 miles offshore, got a little bit of rain and some wind, but no big deal, and we were able to launch about 7 or 8 days later.
It was just so unique. It was very challenging. At the time, I probably wouldn't have called it my favorite, but now, looking back, it's one of our favorite stories to talk about.
Winters is part of a team of about 40 people supporting launch at the 45th Weather Squadron. That's in addition to personnel at Johnson Space Center's Spaceflight Meteorology Group in Houston, the Marshall Spaceflight Center in Huntsville, and the Weather Office here at Kennedy. But the working relationship between the launch director and the launch weather officer is critical.
We do a daily weather tag-up every day, every Monday through Friday, every day for about 10-15 minutes. Doing it daily with her is really helpful, not only from the people processing the vehicle at the pad, but builds that relationship between she and I that is very critical on launch day.
Range weather.
Weather has no constraints for launch.
Thank you, Kathy.
There's been times we've been in some tough situations, and I think Mike can tell just by the sound of my voice, what I'm feeling, what I'm thinking about a particular situation. And so he knows if I'm getting more concerned about something just by the tone of my voice.
NASA will never control the weather, but a talented team and strict safety guidelines will always help protect the nation's spacecraft and crews. There aren't many fire stations in the world with a fleet of armored personnel carriers available. But there aren't many fire stations that have to serve the Space Shuttle fleet and its astronauts either. NASA's Kennedy Space Center firefighters used 4 of the tank-like M113s to protect them and the astronauts in case of an emergency. On launch day, 2 would stand ready with teams of firefighters inside to dash in and rescue the astronauts. Another was based near the launch pad, empty, set up so the crews could drive away from danger themselves. The 4th was a spare.
Well, the reason for the M113s is for our rescue team, for the astronauts, we needed an armored vehicle in order for us to go from where we're stationed for launch to the pad and then up to the top of the pad to perform a rescue of the astronauts.
An M113 weighs 11 tons and is steered with 2 levers that control the respective track. With its rumbling 6-cylinder engine, the vehicle doesn't accelerate so much as lunge, but it can go practically anywhere and offers considerable protection. It's also amphibious, so it can go into the water and swim, although that aspect is rarely employed for Kennedy's vehicles.
This just gives us the protection from whatever environment we may be going into and then be evacuating from in an emergency. The driver themselves, they are squeezed in there like a sardine into where the drivers are. It's very difficult to drive the M113 with your full protection on. With a mask on, with a helmet on top of that, with the hatches closed on the M113, the driver's field of vision is very limited. They're looking through about a 6-inch by 2.5-inch prism as they're driving down the road or going to the pad. During a launch, we're stationed about 9/10 of a mile from the pad. We're the closest people, humans, to the pad when the shuttle launches. Right around T-minus 10, we will don the rest of our gear, put our air packs on, we'll get inside the M113s and we'll call what's button them up. We'll close all the hatches, we'll close all the ramps. We go on our intercom system so we can talk to each other within the M113, but also we have radios that we can hear out to the NTDs if they were to call us up for an emergency. They kind of keep us informed of what's going on at the pad, because other than the driver and one person that's standing in the commander's hatch to see, no one else can see what's going on. We don't actually know it's launched until you see it light up inside the M113.
Every astronaut that has gone into space on a shuttle has learned to drive an M113 during training. Many have driven them several times. The training was a standard part of the Terminal Countdown Demonstration Test, a launch day dress rehearsal known as TCDT.
We get them in there, we go through the procedures, we go through the capabilities of the M113, and then they each get a chance to actually drive the vehicle in an emergency situation where they're driving it over rough terrain, down roads, and I would say every single crew member absolutely loves it, and we always invite them back another time when they're not scheduled for a mission.
The M113s were never used in a launch pad emergency, but were based near the launch pad for each launch of the shuttle program's 30 years. Although never called on, the firefighters who stood ready never felt that training or machinery were wasted.
We are the only country in the world that has a specialized rescue team for the astronauts. So yes, all of us, and I think I can speak for the whole team, are very proud of what we do and what we accomplish here and what we protect. I mean, we're protecting, you know, the United States space program and their astronauts.
One of the most significant updates for NASA's fleet of space shuttles was the installation of the Multifunction Electronic Display System, or MEDS, in the shuttle's cockpits, making the orbiter safer and easier to fly. The glass instruments gave the cockpit a unique appearance, which suggested its well-known name, the glass cockpit. The new display system improved the handling of the vehicle using easy-to-see flight information, such as the attitude, altitude, speed, and many indicators the astronauts need to know during liftoff, landing, and for navigation. The electronic system included 11 full-color flat-panel display screens in the shuttle's cockpit. The screens replaced 32 gauges and electromechanical displays and 4 cathode ray tube, or CRT displays. It's 75 pounds lighter and used less power than the older system. NASA research eventually led to the Federal Aviation Administration's certification of electronic flight displays, and MEDS became mainstream equipment on all commercial aircraft. What's important on a commercial airliner also is beneficial to the astronauts flying the shuttle. Space Shuttle Atlantis was chosen as the first orbiter to receive the glass cockpit during its 1998 modification period, and lifted off with its new cockpit display on the STS-101 mission in May of 2000. Shuttle Endeavour was the last spacecraft in the fleet to be outfitted with the electronic display and made its first flight with the improved system in August 2007 on the STS-118 mission. The glass cockpit still remains one of the most important.
You know, the first-time Challenger, you know, when you're looking at that fireball in the sky, you know you're watching 7 people give their lives for something they believe in. That's gut-wrenching. And the same with Columbia. The loss of life, of course, is the #1 thing that sticks with you. I mean, you never get over that, and you always put yourself in the family's shoes and friends, and you feel the same sympathy anybody in the public would feel.
Some crews you get to know very well. When you see the shuttle launch and you know you have friends on board and people that you've interacted with for you know, a period of time in the lead up to launch, it really makes a difference because you know there are men and women flying on board that have families, that have children, and it makes it all that much more real.
The news media would see its own numbers grow and adjust to new forms of communication, including the advent of news channels and the revolution of the internet with its own specialized brand of reporting.
When I first came down from my college newspaper, I had a manual typewriter, and you'd read the story to an editor, you know, and you're writing for the next day paper, and there was this huge delay between, you know, when you did a story and when it actually showed up in print. And as the shuttle program evolved, cable news networks began, and all of a sudden you evolved into this 24-hour news cycle.
The days of going out and covering a launch and writing a story for the next day's newspaper are gone. We're finding ourselves being sort of like I play a TV reporter on the internet.
For the space enthusiast, for someone who's already interested in this and would follow it anyway, even if it was by magazine or whatever, it's a great thing for them. Because with all the blogs that are out there and the web presence of magazines, newspapers, television, you can get an enormous amount of information that would have been much more difficult to get before.
Because they can ask questions, they can participate, they can get into it.
NASA also began broadcasting on its own network during the shuttle program, originally called NASA Select, now called NASA TV.
Believe me, when I started in the business, radio was the big thing, not TV. TV was trying to catch up with what radio was. So I'm seeing it all change.
People are very curious about what is going on. And so that's a good thing from a public outreach standpoint. It's really good to have that kind of interest in our launches here.
Although they found increasingly advanced ways to cover the shuttle itself remained the center of attention and a touchstone for many societal changes too.
The same shuttle orbiters were used to assemble the International Space Station that is made up totally of international partners who in the last 60 years were at war with each other. Bitter enemies of the United States when our parents grew up, now getting together on the space shuttle and building almost a 1 million pound facility in orbit.
Space exploration is expected to remain a focal point for news media, just as it has in the past.
Again, I think all coverage will get more personal to the audience. I think people will demand that they get the freshest and the latest and that they will be able to participate. And you can do that on the internet. And I think it's going to get more and more and more that way.
Hi, my name is Dr. Emily Schaller, and I'm here at NASA's Wallops Flight Facility on the eastern shore of Virginia. We're here because NASA is using airplanes to study hurricanes. The mission is called HS-3, which stands for the Hurricane and Severe Storm Sentinel. What's a Severe Storm Sentinel? It's actually a remotely controlled airplane called the Global Hawk Unmanned Aerial Vehicle, or UAV. Pilots fly the plane from a cockpit on the ground. NASA is using these Global Hawks to study hurricanes in the Atlantic Ocean by flying over and around them. The Global Hawk can fly for very long periods of time at very high altitudes. It can fly almost twice as high as a commercial jet, and it can fly for over 24 hours without stopping. That's why scientists are using the Global Hawk for the HS-3 mission, so they can continuously study storms as they develop. Forecasters have a pretty good idea of where these storms go, but what they want to know is, will they grow? We spoke with NASA mission scientists about how the Global Hawk will help improve their understanding of hurricane formation and growth, and why it's so important for us to learn more about hurricanes.
The Hurricane and Severe Storm Sentinel has a goal to try to better understand the processes that control the intensity of storms. The ability to predict the intensity is very important because it impacts people in the coastal zones who, if they're anticipating, say, a tropical storm, a Category 1 storm, and they end up getting a Category 3 storm, it makes a big difference in terms of their ability to prepare and deal with the storm consequences.
And this is really important because a category of a hurricane is the intensity of the winds associated with a hurricane. So a Category 5 hurricane is much more destructive than a Category 1. So being able to predict the difference between just a tropical storm, a Category 1, up to a Category 5 is really, really crucial to saving lives and lessening damage and so forth, particularly saving lives.
The benefit of HS-3 compared to any other hurricane mission is the fact that we have these planes able to fly upwards of 24 hours, and being able to monitor a storm for that long period of time and getting constant data, we can actually catch changes in the storm.
We will use 2 Global Hawks. One Global Hawk flies over vast areas around a hurricane. It measures the environment that a hurricane is embedded in. And then the second Global Hawk, instead of sampling the vast area, it goes right in to look at the eye and the eye wall and the inner core processes of a hurricane.
The Global Hawk unmanned aerial vehicles flown by NASA were originally built for the military and used for flight testing at Edwards Air Force Base in California. When the Air Force was done testing these models, they were transferred to NASA, which turned the planes into airborne laboratories to study the Earth. NASA flew its first science mission with the Global Hawk in 2010.
The Global Hawks are really a new aircraft for doing hurricane studies. Manned aircraft typically fly for, say, 8 to 10 hours when they do a research flight. Of that 8 to 10 hours, you may have 4 hours or more just getting to and from the storm, so that in a typical flight you only get 4 to 6 hours actually sampling within the storm. With the Global Hawk, we can get 3 times, sometimes even 4 times as much as you can get with manned aircraft.
Now this plane can fly to 65,000 feet. It can fly 13 miles up. It can also fly for nearly 30 hours. So this plane can take off here from Virginia, on the coastline of Virginia, close to where hurricanes form. It can fly all the way to Africa. It can spend about 10 hours on the coastline of Africa and then fly all the way back. There's no plane that can do that in the NASA vehicles that we have.
Because the Global Hawk can fly so high for so long, scientists can study larger areas of the Earth for longer periods of time, in places where planes with pilots on board may not be able to reach. We spoke with pilot Phil Hall about the Global Hawk and what it's like to fly the plane without actually being inside it.
So the 2 Global Hawks that we're flying for HS3, Air Vehicle 6 and Air Vehicle 1, from a pilot perspective, it's a very different aircraft. We don't have any rudder pedals or a control yoke. We actually use a mouse and keyboard. We actually have a control room on the ground. We have 2 of them now. We have one at Edwards Air Force Base in California, and we have one here at Wallops Flight Facility in Virginia. So it's basically like a trailer. It's been specially designed for Global Hawk. It's full of computer systems that can talk to the aircraft. So we can connect to the internet, and all these satellite products of lightning, the storm from satellite images, we're able to download that almost real time and use that to actually navigate the storm. For the first part of the mission, we actually fly the aircraft from Wallops. And once we get about 2 or 3 hours into our flight, we actually transfer control of the airplane back to Edwards Air Force Base, NASA Dryden Flight Research Center. It's very different from any other kind of aviation operation in that we have pilots on both coasts, and we can actually transfer control of the aircraft during the flight to the other pilots. And when you have these long missions, like 26 or 27 hours, one person can't sit there for the entire flight. So we actually have 3 or 4 shifts of people that come and go to man this aircraft.
Now, pilots know how to fly planes and they can tell the plane where to go, but how does a pilot actually know where to go? You have to have scientific information. Now, the scientists sit in a separate trailer. We have computers sitting in front of us. We bring in satellite information. We bring in forecast information. And because weather can change so fast, they can collect that information, interpret it, and then relay it to the pilots and say, well, instead of going over to this point, why don't you go over to this point over here, which is where we think the eye has relocated. So it's a great team between the scientists and the pilots to actually get the most information you can out of a flight.
How can you become involved in our mission? You can follow the plane too, just like the pilots and scientists do, by participating in live chats, where you can get live updates on where the plane is flying right from your own classroom.
You can definitely be a part of our mission by actually being able to look at the same screen we're looking at. I'm looking at where the plane is flying with respect to the storm, and you have access to the same data I get to look at. You have access to see the plane's altitude, you can see the wind speeds, you can see the wind direction, and you can chat live with pilots, with forecasters, mission scientists, and we're looking at the same thing you are, and that's just really exciting to know that you can ask us any question at any time, and we are right there looking at the same thing.
To learn more about our mission, visit nasa.gov/HS3. See you next time on NASA Airborne.
help us.
But we had no visual of which fires were burning where.
We have to learn from this. We can't tolerate this level of damage, this many deaths.
The key factor now is how can we make use of our NASA data?
To see the fire we're fighting, we use the NASA MODIS satellite system.
Okay, copy that.
To be able to put in instrumentation ahead of a real wildfire is almost impossible to do.
There we go.
One of the basic tenets of NASA was to study the Earth, study the home planet. So fire is an important role player, whether it be with the atmosphere or the environment and its effects on vegetation. So fire just becomes a natural subject for the study of Earth processes. NASA data and NASA modeling efforts and NASA science capabilities, which derive from our satellite orbital assets and allow us to basically cover the full spectrum of fire, from predictive analysis, active fire monitoring, to post-fire rehabilitation and recovery.
It was a normal night, and then my phone rang at 12:30, and it woke me up. You could hear the wind howling.
I started getting texts in the middle of the night, people asking me if my parents were okay. About 2 a.m., I get a text from my boyfriend who was out of town, and he said, "Are you okay?"
Fire medical dispatch. County train state of fire, go ahead.
We see a fire in the distance in the Napa Hills, just north of the city of Sonoma.
We have a report of a tree and house on fire.
So I called about 10 minutes ago. There's a house on fire right next to the house we're staying in.
I'd smelled smoke. Went out on the front porch, and the sky was glowing orange and bright. The wind was blowing like 40 or 50 miles an hour, and the fire was close.
Vegetation fire, City of Calistoga, Highway 148 crosses Tubbs Lane.
911 fire emergency.
We got another fire.
Okay, I'm sorry, we can't even take the calls anymore.
Can you find anybody that could come in and help us? Anybody, all hands on deck, all hands on deck.
I was the division chief in charge of central operations in the Sonoma Lake Napa unit. One of my responsibilities was the oversight of the 911 dispatch center. As I drove into the command center, I passed numerous fires on my way in. I arrived, and for the next 30 days after that, I never left.
The Tubbs fire basically started late evening between 8:30 and 10 p.m. on a ridge between Napa and Sonoma County, the wine country of Northern California. High winds were blowing from northeast to southwest. We call those Diablo winds. Some of the modeling that was derived from our Landsat data and micro-terrain relief modeling indicated that the winds at the summit were blowing over the ridge at almost 90 miles per hour, with sustained gusts above 70 miles per hour. The fire started from the downed power line or a transformer that was affected. And then with these 90-mile-an-hour winds, there was no way anybody was going to control that fire. When it got into some of the more developed urban communities, such as the Coffee Park area, because of the configuration of the winds blowing through that cityscape and the angular momentum created by the building structures, we created these fire whirls or fire tornadoes, which therefore burn or have speeds of up to 200, 250 miles per hour, burning through the community. So that's even pushing fire even hotter and into this urban environment that's composed of building materials, chemical agents in people's garages. So it wasn't just being sustained by vegetation burning at that point, it was being sustained by structures burning in progression down the fire line.
Our intelligence for the Tubbs fire was all based on the 911 reports we were receiving and the radio reports that we were getting from our fire resources and our law enforcement officers out in the field. But we had no visual of which fires were burning where or the magnitude of the incident. When we started getting reports of houses on fire in Santa Rosa, we couldn't comprehend that that could be the same fire that was burning in Calistoga because of how quickly that fire burned. And if we had had a bird's eye view, some kind of imagery so that we could get a picture of exactly what we had, that would have been a game changer. We're actually using some of the National Guard's manned and unmanned aerial assets so that we can practice the surveillance of our fires.
Testing. That aircraft and gimbal line of sight.
One of the major things that we have them help us with is some of the perimeter mapping and determining the exact location of our fires.
You ask almost anybody what California is known for, and it's either California burritos or wildfires, one or the other. A system we heavily rely on is the MODIS satellite system that is provided by NASA that does hotspot detection on the Earth's surface. And we use that to see in near real time where those hotspots are of that fire that we're fighting.
Okay, we got it.
And then we bring in track data and other layers to basically build that combined picture.
That's it? Okay.
First responders, they want to know which houses have been damaged as quickly as possible. And the smoke may or may not have been cleared. But using radar, we can see where those houses are and where we maybe need to focus our efforts based on how a wavelength might bounce off of the surface. We can actually see through smoke and clouds. We can see things like vegetation structure or building structures.
We're going to support the North Ops, South Ops for fire season, which we're now pretty much defining like April to New Year's Day of next year.
We'll have a pretty good idea what the fire's doing early on, like on the campfire, where it starts so quickly and you see what's in front of you, but you have no idea what it's doing anywhere else. Like, that's where we could come in and provide a much better picture. And so I have NASA MODIS and VIIRS stuff, which we always use on Google Earth. You can kind of see the streets here. This is a neighborhood totally burned down. And CAL FIRE, they weren't used to being able to see through the smoke. The perimeter was right here, and they see right here there's a raging fire. They know the fire is now way out there.
We got it up on all these over here.
Remote sensing is really important for the mapping of those incidents, and then also to help us figure out where those hot spots are.
We're outside of our 30-mile limit. We've got a fire out of our right wing towards the north.
CAL FIRE, go ahead and report it.
Prior to having the capability, we would draw by hand basically where the fire perimeter approximately was. Now, with the MODIS data being pulled in, we're able to see irrefutably where that fire was last known to be.
So look, here's what it looks like. So here's
remote sensing application has been a game changer in allowing us to see real time where our fire is. So our operations folks are able to make tactical decisions real time based on where our fire truly is.
Our primary objective is structure protection and just trying to stop the spread of the fire into the adjacent houses.
Looks like hundreds of homes possibly.
Hundreds of homes. We just got here this morning. I can't even give you a number.
There was a second phase where when the winds died down, we continued to have a more typical fire event, which was driven largely by the fuel loading in the landscape. As a result of the work that we did in collaboration with NASA, we were able to really separate those two events because we had really good data about wind levels and the time.
Our plants have been affected by years of drought. It means that we have years of dead fuel buildup in the state. It's called fuel load, and it's basically how much plant material there is within a specific area. And as that continues and continues to increase the amount of fuel loading, our fires burn hotter and more intense and quicker.
It's in the relationship between topography, fuels, and climate that drive a fire across the landscape. The heat generated from the fire, especially in steep terrain, is what's propelling these fires forward. And then you add to it a growing wildland-urban interface, we are seeing just more impactful fire events and hence the increase in megafires.
The key factor now is how can we make use of our NASA data in the recovery operations?
We need to understand why some people lost their homes and other people didn't, why some watersheds burned. We need to understand the intensity and the damage done by the fire.
See now.
So this is the post-fire imagery?
Matching up with what we're seeing now, a lot of this area within our view was burned.
So what was the fire direction we're looking at it here? I mean, kind of from this direction, burned down and...
The fire started down in the canyon.
Okay.
And it actually burned to the east.
Right, okay.
And then the wind shifted and this part of the canyon burned in the topography-driven fire later on.
Okay.
Yeah.
After the fire burned, we needed imagery right away to understand the damage. Because now, several years after the fire, a year and a half, there's a lot of regeneration. If you have ladder fuels, that's the fuels from the ground up to the canopy. If the ladder fuels are dense, the fire's going to burn hotter, you're going to have more damage. And with LiDAR imagery, now we understand that.
The way that LiDAR works is it will tell you the distance from the sensor of each point return. So when you send out a pulse and you get it back, you know exactly the distance that it traveled. And if we did that with billions of points, we can actually recreate three-dimensionally all of the structures in a space. We can construct the vegetation, we can even construct to the leaves on the trees.
A fire that burns through an ecosystem will start out as a ground-based fire primarily, burn up through vegetation communities and get into the crowns of trees. That's called ladder fuel development, which leads to a greater chance of very high severe wildfire.
We can now map the ladder fuels and where they occur across the landscape. Then we can compare where they occur next to homes or hospitals or roads. And with those things together, we can prioritize treatments for fuels. So we're going out of this study really well armed to be able to manage fire risk across the landscape.
After the fire, when I drove through the Coffee Park neighborhood, which was a half a mile from my house, the thing that struck me was how much it looked like images of Hiroshima and Nagasaki during World War II. All that were left were standing chimneys, brick chimneys. Everything else was totally consumed, burned to the ground.
We've been using wildfire as a tool for millennia. We've been using it for cooking, to grow crops and nutrient cycling. So we've had this relationship where fire is a tool, but at the same time, it's also a natural disaster, right? We don't think of hurricanes as tools.
I had revelation that prescribed fire was an important part of restoring ecosystem management over about the last 10 or so years, and we need to make it a consistent part of our management of our resources. Introducing prescribed fire into that ecosystem allows us to remove some of those underlying ladder fuel components and allows that forest floor to kind of open up and not have the propensity to burn in dramatic wildfire style.
This is part of a very large project that's called the Fire and Smoke Model Evaluation Experiment, and it's as close to a wildfire as you can get. The objective is to collect a suite of data to both evaluate and advance our fire and smoke models. To be able to put in instrumentation ahead of a real wildfire is very dangerous and almost impossible to do.
NASA funded our previous project that actually allowed us to build, this prototype with the fire model. It's focused not just on the prescribed burns, but also on wildland fire. We were able to get, the new forecast run just, before the briefing, and just right after the briefing we get the first results. So we had an idea about the wind speed, rain.
Winds aloft are going to be start to crank this afternoon, so there's going to be a sweet spot early this afternoon.
So what time are they thinking of igniting?
So this part of the unit over here, we're looking at around 1300, 1400, letting the sun get on it. This is our one concern area where we have continuous fuels. We're going to send the hot shots that are rolling out of here right now.
We see all the valley over there. We should be in a good spot to set up our truck in the LiDAR. That's gonna be a more intense burn, but also the plume should be going this direction, so we will be able to really have a good angle.
Right here, and then transition is gonna be the
I think we have so much better chance, for the fire to take off and kind of, start moving, freely after the ignition. So from that standpoint, it's gonna be, really interesting.
Air temperature, 65.4.
Attention on the crew net, attention on the crew net. The helicopter is airborne and they are igniting test fires at this time.
So topographically of where they're going to go push and drop another barrel of gel is in a slot canyon right back over there. And so it should follow this, maybe be over it, but we'll be underneath and be able to watch it just go right over us. Cool. So.
A lot of smoke, so I think we'll get something out of it.
We had to move back up the hill here to clean air while the column folded over on our location there.
So I'm super happy. I kind of believe that our forecast it was really spot on in terms of how strong the winds are over this region. The same in terms of the plume location. I mean, you see that we are actually really close to the plume, and that's what we wanted. 5 years ago, when we were talking about real-time coupled fire atmosphere forecasting, and people were saying that, well, that's impossible. 5 years later, I mean, we have completely different computational power, to execute, those forecasts. I mean, we can really do that.
That's really the takeaway message for this whole program, is that he was able to initiate his model today and yesterday and get a forecast that matches what we're seeing.
So I'm super happy that NASA had a faith, in this whole idea. It's great, to see that, running, working, and I hope that, pretty soon, other people will be using that, and it will be very helpful in designing prescribed burns, but also, in terms of fighting wildland fires.
This is the home site right here. This was the garage right here, and then you can see the patio in the back. The fire was coming from the northeast. Once it hit that stand of Douglas fir.
Up on that ridge out there.
Yeah.
500 yards out or something.
Then it was all over.
We started seeing the first MODIS fire detects from our MODIS satellite and VIIRS satellite, but primarily MODIS at the nighttime overpass, so a little bit after that. Yeah. It'd be great if we can get some of that information to earlier detection capabilities to mobilize resources to evacuate people.
In a widespread disaster like this, people appreciate each other in a different way. They chose to come together to help each other instead of trying to everybody's solo it. And doing so made us all stronger as a community.
With climate changes, fuel loading changes, we are seeing an earlier start to fire season, and we are definitely seeing a longer length of fire season.
We have to learn from this. We can't tolerate this level of damage, this many deaths. Our small study we did with NASA is turning into really important tools for other communities throughout Northern California.
Sitting on top of this Falcon 9 rocket at Launch Pad 39A at the Kennedy Space Center is NASA's latest instrument that will be sent to the International Space Station. It's called SAGE-3, and it will be used to monitor and measure something that is important to the entire human race and every other living thing on the planet: Earth's precious atmosphere. For many of us in the general public, this looks like just another one of the hundreds of launches that we've seen NASA perform over its 50-year history. But for the scientists, engineers, and support staff who have spent years of their lives preparing for this moment, this launch represents the culmination of all their efforts. It is impossible to calculate how much planning, execution, and sacrifice this team has made to get this instrument to this point. But suffice it to say, there have been many sleepless nights and long hours getting everything just right. So it's easy to understand why so many of these engineers and scientists are holding their breath at this moment. Although this is not the first SAGE instrument to go to space, it is the latest and most complex, since scientists first realized that Earth's fragile atmosphere was thinning further and in need of monitoring. Because this mission is so important, the tension is high for the SAGE team. Have they checked everything? Will the rocket work? Will this mission be successful? They will know in just a few minutes. On this episode of NASA X, we will go back and look at why the SAGE-3 instrument was developed and get a better understanding of what it will be monitoring. We will also follow some of the team as they prepare the instrument from the beginning to shipping, to the clean room, and eventually into space. And we will be there for the launch to see if everything went as planned or if it reaches its final destination attached to the International Space Station. Here in this building at NASA Langley, some very important cargo is being loaded aboard this truck for a special delivery. Inside this container is the SAGE-3 instrument that has been designed to study aerosol distribution in our atmosphere and to study ozone, which is a gas found in the upper atmosphere that acts as Earth's sunscreen. This cargo's first stop is NASA Kennedy Space Center, but its ultimate destination will be 250 miles above Earth, attached to the International Space Station. More than 25 years ago, scientists realized there was a problem with Earth's protective coat of ozone. It was thinning. So NASA and the world community worked together to send instruments to space that could help us better understand what was happening in the atmosphere. Beginning in the 1970s with the Stratospheric Aerosol Measurement SAM instrument, then SAM-2, SAGE, SAGE-2, SAGE-3 Meteor 3M, and now SAGE-3 ISS have all been invaluable in helping understand Earth's aerosols and Earth's thinning atmosphere. The SAGE family of instruments was pivotal in making accurate measurements of the amount of ozone loss in Earth's atmosphere, and also played a key role in measuring the onset of ozone recovery resulting from the Montreal Protocol, which was passed in 1987. Even after 25 years, the SAGE instrument is still the best instrument for the job, and now, with updated hardware, NASA is preparing to send the third generation of the instrument into space, this time attached to the International Space Station. But before it can be placed on a rocket bound for the ISS, SAGE-3 will have to be retested, making sure any components were not damaged during its journey from Virginia to Florida. That work is being performed in a clean room here at NASA Kennedy's Space Station Processing Facility. The team will go through procedures to make sure that SAGE-3 is in perfect working condition.
This week the team is working to complete the full functional test of the instrument payload. And what that does is it verifies the instrument's, the subsystem's functions and also the test the interfaces between the subsystems. And it's in the clean room because we have to meet contamination control requirements. And those requirements are really important because we do not want any of these, the optical or the radiator surfaces could degrade over time if there's surfaces are contaminated.
To fulfill its scientific goals, SAGE 3 is equipped with a set of tools with a total mass of about 1,162 pounds. Its most important payload is the Sensor Assembly Instrument, a grating spectrometer that measures ultraviolet and visible light and has a 2-axis pointing system. The Sensor Assembly Instrument contains the Charge-Coupled Device Array Detector that enhances measurement capability and may allow for new experimental data products like methane, bromine monoxide, and iodine monoxide, as well as measure larger aerosols. SAGE 3 is also fitted with the Interface Adapter Module, which is characterized as the brain of the instrument payload, the Disturbance Monitoring Package, the Hexapod Pointing System, and the Instrument Control Electronics Box, while the Hexapod Pointing System will act as the legs of the payload, keeping the instrument level in orbit.
Basically, we're exercising all the parts of the payload. We'll do all the things that we're expected to do on orbit. We'll take science data. We have a light source simulator that we use to simulate the sun, and it allows us to take science events. We'll move the hexapod, we'll move the upper platform to different locations. We do a range of motion tests just to make sure that it can cover all the extremes of its envelope. You know, we have some redundancy, so we'll check the main side and the redundant side and make sure we can do things like upload software and run certain commands, pretty much putting the payload through its paces. And we've done this several times along the way, and then we'll take the data and compare it to the previous tests we've run and make sure that everything is in line, all the data is consistent, and we're getting the results that we expect.
When final powered testing was completed, the instrument payload and the Nadir viewing platform were handed over to SpaceX for installation into the Dragon trunk of the Falcon 9 rocket, leaving the SAGE 3 team waiting for a launch. Even with SAGE 3 in the hands of SpaceX, the team continued to go through scenarios preparing for an eventual home on board the ISS.
When we first get mounted to the space station, we actually will be running out of here 24/7 for approximately the first 2 weeks as we power on each subsystem. We've got 5 subsystems, so we power each one up about once a day just to make sure it powers up correctly, check the status of it. And then we'll be doing calibrations, make sure the CCD, which is kind of a fancy digital camera, the main part of the instrument, is calibrated correctly, it points correctly. So we'll be doing that all out of here about 24/7 with a crew of about 8 of us. And then once we finish the commissioning phase, then we'll go more into the routine operations where on a daily basis we'll have someone come in here, they'll check the health and status of the payload, send the commands up that we need to make sure it's executing correctly, and then we'll be based in another building here at Langley. We'll be down at Kennedy. I'm very excited, so I'm going to have our whole mission ops team down there, and we'll watch it launch, and then we'll hightail it back here very quickly. It'll take about 2 to 3 days for it to dock to the space station, and then once it's docked there, the space station has about up to 30 days to actually pull us out of the Dragon trunk of the SpaceX launch vehicle and install us on the outside of the space station.
After arrival at the ISS, SAGE 3 will be robotically mounted externally on the station without the need for astronauts to perform a spacewalk. The instrument will orbit between 239 and 257 miles above Earth's surface at a 51.6-degree inclination, with nearly a 3-day repeat cycle. This is important because the station's orbit is expected to help maximize the scientific value of SAGE-3 observations. The main scientific objective of the SAGE-3 mission will be obtaining high-quality global measurements of key components of Earth's atmosphere. In particular, the instrument will assess the state of recovery in the distribution of ozone and will re-establish the aerosol measurements needed by both climate and ozone models. The view from the space station will give researchers a new perspective of atmospheric composition and will allow scientists to monitor the health of the ozone layer and track recovery of stratospheric ozone since ratification.
And what the surface area density. Those are two important properties for modelers to use. So the aerosols that we're looking at are in the stratosphere. And the primary effect there is when say, a volcanic eruption goes off and you see these beautiful sunsets. That's one thing that people can immediately connect with. But it's like adding an extra blanket at night on a cold night. It will prevent some of the radiation from leaving. The aerosol layer itself heats up a little bit. But it's also like putting on a bit of sunglasses as well. On the surface, you get a little bit of a cooling. Very subtle effects, but if you're looking at the long history of temperature change, say on the surface, you're going to see a lot of variability in there, and that's often highly correlated with the amount of aerosol.
The sulfur dioxide, once it gets into the stratosphere, all the big rocks and everything, that's regional. It gets washed out, pushed out, whatever. It gravitates out locally. Stuff that we're looking at is the SO2 that gets in the stratosphere, changes to sulfate particles, condenses and forms micron size or less sulfuric acid droplets. As the sunlight's coming in, those particles absorb some of the radiation and scatter back some of the radiation. These little micron-sized particles or less. So the scientists are going to be happy about getting the aerosol data in case we do have another volcanic eruption. But then ozone, it makes the gold standard ozone profiling, and they're all waiting for that because we want to see if it's recovering. You know, it's all tied together. So we're not only going to check the trends of ozone, but we're going to be able to be up there for the aerosol and studying aerosol.
Moreover, if there are any new changes to the ozone layer, the data will help the scientific community identify the cause and assess the impact of the changes. Understanding the stratospheric ozone changes is crucial to determine whether the recovery of the ozone layer is progressing as expected since the Montreal Protocol was enacted. After all their hard work, the day the team has been waiting for has finally arrived. Launch day.
T-minus 1 hour, 15 minutes.
Although most are confident, launches can be stress-inducing. Thousands of hours and millions of dollars have gone into this effort, and for now, everything is out of their hands while SAGE-3 attempts to make a perilous journey from Earth into space.
So today is kind of like the ending of one chapter and the beginning of another chapter. So all the work that we've put in to go ahead and prepare the payload for launch and for on-orbit operations and for processing the science data, those have been complete. And so we've successfully And so the aerosol measurements continue a long-term trend, developed with the SAM experiments in SAGE 1 in 1979, SAGE 2 in 1984. The SAGE 3 we flew on a Russian Meteor 3M satellite in 2001. And so that data is a good long-term stable trend baseline that can be used by the science community. So, man, we're ready to go. Ready to go ahead and complete the installation, which is done robotically. I kind of look at that and I go, when I was a kid, the idea of an orbiting laboratory and then a rocket without a human driver and then robots basically taking care of the assembly on orbit, that was all science fiction, and that's like complete fact today. And so we're kind of on the cusp of ready to go off and do that. And it's like, wow, okay, this is cool. Our team is ready, the hardware is ready, SpaceX is ready. The weather, I don't think it could get any better than this. So I think we're ready to go.
As crowds gathered and the SAGE 3 team anxiously watched the countdown clock, an event typical in many launches occurs. A delay.
Hold. Just had a hold in the countdown.
Fortunately, the problem was addressed quickly, and early the next morning, SAGE 3 was on its way.
3, 2, 1. Ignition and liftoff of the Falcon 9 to the space station.
Soon after it arrived at station, the instrument made its way to its final position, and the team began receiving valuable data so important for the entire human race. The instrument continues to work perfectly, with data streaming in, adding to the global database of information about our atmosphere. This data is not just being studied at NASA, but is being made available to researchers around the world as well, helping us keep an eye on our fragile atmosphere. After years of hard work by so many dedicated people, this mission is a success. From humble beginnings in 1979, the SAGE saga has evolved into a state-of-the-art instrument capable of providing data that will be useful 50 years from now. NASA will continue to build on the success of SAGE 3 and share the journey of scientific exploration with the world.
My land-covered career really started in 2002 with biggest wildfire in Oregon's history, and that was the Biscuit wildfire. I, at the time, was doing botany surveys and looking for rare plants or rare mushrooms, and so I was spending a lot of time out on the forest looking at and taking photos and doing the documentation that a scientist or a land manager does. When that fire happened, it changed everything, because we all had to react to this fire that was burning up some of the places that I'd literally been the day before. And it was mapping what was there and what was under threat, but it was also mapping the effects of the fire. We needed to find a way to look across 500,000 acres. And the only way that we could really do that was satellite data. If we can't get out and actually measure every single thing, what are we missing? And that's where citizen scientists can actually come in and really help traditional scientists to better understand what is happening around them, but also fill in these gaps.
The Global Learning and Observations to Benefit the Environment program is an international science and education program. It provides students and the public with the opportunity to participate in data collection and the scientific process. The Globe Observer app is one of these opportunities, allowing citizen scientists and students to take land cover observations around the world and submit them to a larger database. But what exactly is land cover? Dr. Eric Brown de Colston of NASA's Goddard Space Flight Center explains.
Land cover is really the basic form of the landscape that we have around us. So whether it's a forest or a desert, but it's really one of the components of the landscape that we can study from space.
Dr. Peter Nelson is a scientist who uses land cover imagery in his research.
I am a remote sensing scientist who studies land cover across the globe. I like imagery to make maps of land cover and try to quantify what covers the Earth. Sometimes a satellite can't see what's happening underneath a tree canopy or what's happening underneath cloud cover. And so we really need people to go out there and to take these photos, to do these observations, to help fill in where a satellite can't actually make some observations.
Just like any digital photograph, land cover images are